So, welcome to FROSTy Brews. We're going to have some fun today. I know this is script week, but this talk is entirely about avoiding scripts at all costs. So, a little contrarian. If you guys want to follow along, we're going to be working through my Python Frost implementation. So let's get started. So first of all, let's just kind of set the table. What is Frost? Why do we care? What's the base protocol? What are the extension protocols? So Frost is a way of doing a T of N multi-signature key completely without scripts. So we can have a Taproot key on chain that looks like a single key and has a single signature, and it's actually created with multiple parties. So for example, we could have a 3 of 5 key where 3 participants are required to sign, and there's 5 participants total. But on chain, it looks like a single key and a single signature. So this is really nice because you get less fees because you have less keys in the script. We have like a constant scaling factor, and we have a lot better privacy because when we go to spend these coins, we're not revealing the configuration for the setup. And if you have an unusual configuration, that can actually kind of fingerprint who you are. If you're like one of the only people doing a 5 of 58 or something, it's much more likely that it's you if that shows up on chain. Now, the newer thing that this talk is about is the FROSTy Brews, which is what I just described as the base protocol. But what we can also do is we can take these techniques from Shamir secret sharing, proactive secret sharing, and dynamic secret sharing, and we can change our shares of the key without changing the underlying secret. So this is useful if you're defending against a mobile adversary where somebody starts off compromising one participant and then maybe a few weeks later compromises another participant. Well, if you've refreshed the shares in the interim, now the attacker has to start over from the beginning and get the first participant's share again. So that defends against this mobile adversary. They have to get a threshold of shares within some time period T. Also, if you lose a share, we have this other protocol to be able for a threshold of participants to be able to send the participant who lost a share some data, and that participant can reconstruct their lost share. And then something you might want to do after that is refresh the shares, because you might assume that the lost share has been compromised. Maybe it's on a phone that's been lost, and somebody gets access to that phone, they can extract the share. So repair and refresh go really nicely together. And again, we're not going on chain for this. We're not moving the coins. We're not paying transaction fees. We're not taking a privacy hit of pulling all the UTXOs into a sweep transaction and linking them together. And we're preserving access to our old addresses. So if we've already generated and distributed addresses with this Frost key, if we had to do a sweep, now we've lost some shares or we've changed our configuration, and the only way to sign from the old addresses is with the old quorum. Whereas with this kind of system, we're able to recover and repair and change the configuration around and always maintain access to be able to sign for any UTXOs and be able to work with any addresses that have already been distributed. We can also add and remove participants, and we can move the threshold around. We can increase the threshold, we can decrease the threshold, all off-chain, no scripts. So to understand how this works, we need to start with a basic overview of Frost, and to understand Frost, we need to understand Shamir secret sharing. So we have this property of polynomials that for every set of n points, there's a unique n-1 degree polynomial that fits those points. So an easy example to understand is if we have 2 points, there's only one line that goes through those 2 points. Line is a 1 degree polynomial, So 2 points and a 1 degree polynomial for the 2 points. Similarly, if we have 3 points, there's a unique parabola, a unique 2 degree polynomial that traverses the 3 points. And we can generalize that to any n points. There'll always be an n1 degree polynomial that fits the points. So let's say we have some points. Let's say we have 3 points and we want to actually get to the parabola equation that uniquely is defined by the 3 points. We need to do something called Lagrangian interpolation. And so what we're going to do is for every single point, we're going to create this Lagrange polynomial. And the Lagrange polynomial has this really interesting property where when the Lagrange polynomial for a point is given the x value for that point, then the Lagrange polynomial is going to return 1. And if the Lagrange polynomial is given an x value for any of the other points, it will return 0. So we can see here in an example, so let's say we have this Lagrange polynomial for L of j, looking at the very bottom here. And if we plug in x of j, it's going to get 1. We're going to get 1 because the m's are incrementing, the j is constant, and then the top left x, we've plugged in x of j. So we're going to keep getting this repeated pattern xj minus xm over xj minus xm, and each time it will equal 1, so we'll get a bunch of 1s multiplied. By the way, if anybody has any questions, please jump in at any time. This is meant to be interactive, and a lot of this is probably going to be a little bit confusing at first. Now, similarly, if we plug in a different one of the other points' x values into the Lagrange polynomial, one of these terms is going to equal 0, and since they're all multiplied together, they're going to 0 out, and we're going to get a 0. So you can see here, like in the middle term on the second row, we have an xi minus xi, and that equals 0, and 0 divided by anything is 0. And then when they multiply together, we'll get 0. So let's look at an example. Hopefully we'll make this a little bit more clear. Well, actually, before we get to the example, the last point here is how do we get our interpolated polynomial? Well, we're going to take the Lagrange function for each point, and we're going to multiply it by the y value for that point, and then we're going to sum those together. And so what's going to happen is when we plug in an x value for a point that's in the polynomial, all the Lagrange polynomials will equal 0, except for the one that has the y point for that point. That one will equal 1. So we'll get L of x equals y. For each x, we're going to get its y value. And the example here will illustrate that. So let's say we have let's say we're dealing with points with x values 1, 2, and 3. So we'll have on the second row here to the left, we have the Lagrange function for the first point, and it's taking the x value for the second point as its input. And we can see that that equals 0 because the first term is 2 minus 2, and so that's going to 0 everything out. Now, let's say here on the bottom left, if we take the Lagrange function for the first point and we give it its own x value, it's going to equal 1 because we're going to get this repeated 1 minus 2 over 1 minus 2. And you can see like the top right term is incrementing. That's all that's happening. We're just in a loop where we're incrementing the top right term through each index, except for the index being the x value. We're incrementing through each point's x value, except for the x value of that Lagrange function. That's where we have the m does not equal j. So on the bottom right, we can see how this comes together. We have if we take each Lagrange polynomial and we add them together and multiply each one by its corresponding y value, we actually have the interpolated polynomial. So if we plug in L of 1, we can see that the y1 is multiplied by 1 because its Lagrange polynomial will equal 1 when it's given its own x, and then the other ones zero out. So we have what we're left with is y1. So we want for x1, when we plug in x1, we want to get y1, and that's what we have. Similarly, when we plug in x2, we want to get y2. And when we plug in x3, we want to get y3. So we're forcing this polynomial to fit the points through this kind of strange multiplication. So we can see how this works in code, where we set the numerator and denominator as 1 to start us out. And then we're going to iterate through each index. In other words, through the x value of each point. So if we have, let's say, x equals 1, x equals 2, x equals 3, that's going to be our index as we go through this loop. And then if the Lagrange polynomial for its own x value is in the iteration, we continue. We skip over it. Otherwise, we set the top part of the fraction to the x value that we are interpolating minus the x value that we're iterating into, and then the denominator, we have the x value of the Lagrange polynomial minus the iterated x value. So that's all it takes to create this Lagrange coefficient in code. And basically we can evaluate the polynomial at any x value by taking the set of x values for all the points and creating this Lagrange coefficient for each one, multiplying it by the corresponding y values and summing them up. The Q is, yeah, so that's a great question. So we're actually doing this in a finite field. So Q is it's actually the curve order, and that bottom line we can see we're doing modular division using Fermat's little theorem there. So that's why we have to mod everything by Q and do this special kind of division. So let's look at an example here. So how we use this in Shamir secret sharing is, let's say I want to split a secret into a 2 of 3. I'm going to set my secret as the first coefficient. So that's A0 is the first coefficient of a polynomial, and we're setting it to 23. And then we're going to generate random coefficients until we have t minus 1 coefficients. So that's the A1 to AT minus 1. We're taking it randomly from the integers mod q. That's the z mod q. And so the two coefficients that we arrive at are 23 and 42. These are just randomly generated. 23 is our secret, 42 is a random coefficient. And then to turn that into polynomial form, we take each coefficient multiplied by x to an increasing power. So what does that look like? We have the first coefficient 23 multiplied by x to the 0 plus our second coefficient, 42, multiplied by x to the 1. And since we're doing a 2 of 3 example here, 3 is t. 2 is t, our threshold. So t minus 1, 2 minus 1 is 1. So we only have a 1 degree polynomial. And then we just sample points. We plug in to get our shares. So this would be like some kind of, you have some sort of trusted dealer that's going to issue these shares to someone. This is how Shamir secret sharing works. Like a lot of crypto exchanges use this to secure their keys. They'll take a private key. They set it as the first coefficient. They generate random coefficients to create this polynomial. And then to create the shares, they simply plug in these x values. To get the first share, they plug in x equals 1. To get the second share, they plug in x equals 2. Third share, x equals 3. So we see we have these 3 shares here, 46, 69, 92. And those are 3 points. The first point, 1, 46. The second point, 2, 69. The third point, 3, 92. So we have 3 points. And with any 2 of these points, we can use the Lagrange interpolation to reconstruct our line equation, and we can evaluate it at 0. And when we evaluate this polynomial at 0, we're going to get the first coefficient, 23. And that's our secret. So we get back to our secret. So what would be nice is if we could do this without having to trust anyone. When you have the previous setup here, if whoever created this polynomial, if their machine is compromised, then you're screwed. We have to have a really secure setup, maybe like a Faraday tent and, shred the computers and do all this crazy stuff to make sure that whoever generated this, the polynomial that they created doesn't leak from the setup. We only want the shares to be exported from the setup. Well, it'd be much better if we could do this without needing any kind of trusted setup at all. And so that's what distributed key generation is, and that's the first part of the Frost protocol, is this thing called distributed key generation. So the setup looks exactly the same as what we did before, where we generate random coefficients up to t minus 1 and create this polynomial. The only difference is every single participant is going to do this, not just some trusted dealer. If we have 3 participants, each one is going to create their own random coefficients and their own polynomial. And this is a link to the Frost paper and the page that this algorithm is on. So what does this look like in code? We just get some 256 random bits, mod q. We iterate over until we get a series of coefficients such that the degree is t minus 1. If the degree is t minus 1, then you're going to have t coefficients, right? Because if you have equation for a line, it's at ax0 ax plus ax1. So that's a 1 degree polynomial, 2 coefficients. So that's why we're iterating over the threshold. So that's how each participant will generate its polynomial. So let's look at a 2 of 3 example. Participant 1 creates the polynomial f1 and gets their random coefficients. Participant 2 generates their own polynomial f2 and their own random coefficients. And participant 3 does the same. So we have 3 polynomials, 3 sets of random coefficients, 1 per participant. Now, we need to make this protocol secure. We need to use something called VSS, variable secret sharing, which is when participants receive their shares, they need to be able to verify that all of their shares are actually part of the same polynomial. Because if somebody's misbehaving and they actually are giving everybody different shares that don't fit the same polynomial, then our protocol is going to fail. So we need a way for each person who receives a share to be able to verify that their share is correct. So what each participant will do is they're going to commit to each of their coefficients. We're going to translate the coefficient into the point domain. We're going to use, so like the same way we generate public keys from private keys. If we have a private key X and we want a public key, we multiply it by the generator to get our public key, G to the X. So we treat each coefficient like a private key, and we derive a public key for that coefficient. So we have G to the AI 0, G to the AI 1, and so on. So we have these, we're taking the polynomial and we're creating this committed form, but we're encrypting the secrets, which are the coefficients themselves. And we're creating this commitment vector CI that has this phi, which is the committed form of each coefficient for each polynomial. So we can see this in code. We go over, we iterate over our coefficients, and we multiply each one by G, and we have our coefficient commitments. So the first participant gets this vector, the second, the third, and so on. They each have these committed forms of their coefficients. So let's take a look at the first participant. They have their polynomial. They're going to derive a share by plugging in x equals 1. They're going to derive another share, and they're going to give that to themselves, P1. Then they're going to derive another share by plugging in x equals 2, and they're going to give that to participant 2. And then they're going to get a third share by plugging in x equals 3, and they're going to give that to participant 3. So participant 1 is taking their polynomial, deriving 3 shares, and distributing a share to themselves and each other participant. And every other participant will do the same thing. So participant 2 will create 3 shares and distribute them. Participant 3 will create 3 shares and distribute them. And the way this looks in code is we're going to evaluate the polynomial. The participant will evaluate their polynomial for x equals 1, x equals 2, x equals 3 until they have one for each participant. And the way the participants can verify their shares is they use these coefficient commitments, and they plug in the x value. So participant 1 will take the coefficient commitments from participant 2 and evaluate the polynomial with the commitments instead of the raw coefficients. And that should equal the committed version of the share they received. The share they received translated into the point domain by using it as a power of G, the generator. So we can see this more clearly here, where let's look at participant 1 received a share from participant 2. So participant 2 had the f of 2 polynomial plugged in participant 1's index 1 to generate their share and gave it to participant 1. Now, we can see how the commitments parallel the top equation. We're just taking the top equation and we're applying G to each term. So if the top one is true, the second row needs to be true. And the third row needs to be true. If the share that the participant received was not generated with this polynomial, then this equality will not hold. When they go to verify their share, it will not be equal. Now, one thing that's important for this to be secure is we need to use something called a broadcast channel, or something that gives us similar guarantees, which is all the participants need to know that they receive the same commitments as everyone else. Because you could actually craft the commitments in such a way that you can induce a participant share to verify, even though it doesn't actually match with like some manipulating how the exponents work and negating them in a specific way. So everybody needs to know that they receive the same commitments. We also need to distribute a proof of knowledge for the first coefficient. The participants need to prove that they know that first coefficient because there's a rogue key attack that can apply here without that proof. So here's in code how we verify the shares. We initialize the expected Y commitment at the point at infinity because it will serve as this accumulator. And then we're going to iterate over each commitment. And we're doing the self.index to the K is the polynomial terms x to the x to the k increasing. So like x to the 0, x to the 1. We're iterating through k, increasing it. So that's the increasing x value for each term. And then we're multiplying that by the commitment. So we're just evaluating the polynomial with the commitments instead of the raw coefficients. And then we're checking for equality. Y is the share that the participant received that they're trying to verify, multiplied by G, and that should equal the polynomial evaluated at their index with the commitments. Because the expected Y commitment is actually a point, is not a scalar. Yeah, so, and then we're multiplying, we're adding all these points together. So only the scalars, the self.index to the K needs to be modded. And then the points are already in the subgroup. So let's look at this from the perspective of a participant who generated, from the perspective of participant 1, these are the 3 shares that they received. They got evaluation of the first participant's polynomial at x equals 1, valuation of the second participant's polynomial at x equals 1, and evaluation of the third participant's polynomial at x equals 1, because participant 1 has an index of 1. So these are all the shares that the first participant will receive. Now, what's going to happen is participant 1 is going to add all their shares together. And when they do this, that's going to equal the sum of all the polynomial terms. We can see that the first polynomial at x equals 1 has a set of terms, and the second polynomial at x equals 1 has a set of terms, and the third one. So by definition, when we add these evaluations together, that equals the sum of the polynomial terms added together. So we're just taking, if you look at the left here, we're taking all the a's and we're just stringing them all together, and we're saying that equals the sum of all the terms on the left-hand side of the equation. So if we have 3 line equations, and we take the x equals 1 and we add up the y values, that will equal the sum of the line polynomial terms. And this, so we see for each participant, they're doing this summation. Each participant is taking the shares that they received and adding them together to get an aggregate share. And if we generalize this, we can see that the sum of any of the shares, any of the sum of the polynomial evaluations is equal to the sum of each participant's polynomial. And so what that means, if we look here at the bottom right, is that now each participant has a share of a polynomial where the secret, remember the secret is our first coefficient, is the sum of each participant's first coefficient. So now our secret is A1 plus A2 plus A3. And participant 1 knows A10, participant 2 knows A20, participant 3 knows A30, but they don't know each other's. So nobody knows this sum. Nobody knows A10 plus A20 plus A30. But now everybody has a share that will reconstruct to that secret, which is what we wanted. We wanted to do Shamir secret sharing without having to trust anyone. Now everybody has a share of a secret that nobody knows. So if a participant I's share, SI, is the sum of the shares that they received, which are the evaluations of all the polynomials. Similarly, our secret, f of 0, is the sum of all the coefficients, all the participants' secrets, their own respective first coefficients. And if we want to interpolate the secret using Shamir secret sharing, we take the share times the lambda times the Lagrange coefficient at 0. We sum them together, and we would get to this coefficient A0 that nobody knows. So in code, most of this is just some validations, but really all that's happening here is we're iterating to aggregate the shares. We iterate over each share and add them together. Now, if all we were doing is this, but when we need to sign, if we had to bring the shares back together to reconstruct the secret, we have the same problem as the trusted setup, where now when we go to sign, we need like a secure, trusted environment because we're computing the secret again. So we actually want to be able to sign for this secret, for this key, without having to bring the shares together in one place. So if our Schnorr signature equation is sigma equals R plus C times the private key, and our private key is our secret, our first coefficient, A0, R is a nonce, then each participant will create this partial signature by signing with their share multiplied by the Lagrange coefficient. That's the second line. And when we add these partial signatures together, the nonces will just add together. So R1 plus R2 will equal the nonce. But when we look at this right side here, we'll have this C times the share times the Lagrange coefficient plus the second one. When we factor out the C, we have share 1 times Lagrange coefficient plus share 2 times Lagrange coefficient. Well, that's our interpolation formula. That's what we use to reconstruct the secret. So what we're going to arrive at is a signature for that secret. We're going to interpolate it into the signature equation without the secret by itself being extracted. So nobody actually learns A0, but we get a signature for A0. So that is, so then you might ask, well, how do we figure out the public key? We figured out shares of a private key and how to sign for them, but how do we know what the heck the public key is? Well, our coefficient, our secret is the sum of all the each participant's first coefficient, A0. So therefore, the public key is the sum of each participant's commitment to their first coefficient. These things are just paralleling each other. We have the private key is the sum of all the first coefficients. Therefore, the public key is the sum of all the committed first coefficients. So in code, to derive the public key, we take each of the coefficient commitments for the first term, and we add them all together, and we get our public key. So that's Frost. That's basically what you see in the Frost paper. We can distribute it in a distributed way. We can sign for it. That's how we can get these multi-signatures without any scripts. There's no Bitcoin script here to make this possible. When we produce this signature here, it just looks like a single signature for a single key, even though it was constructed with these partial signatures. So now we're going to get into the interesting stuff, which is the into the FROSTy Brews. So the first one is share refresh. How do we change each participant's share without changing the secret? Right? Again, this is to defend against the mobile adversary, or to be able to, after repairing a share, to be able to invalidate the lost one. We are going to do our distributed key generation protocol again, except for one key difference. The first coefficient is going to be set to 0, but everything else will be exactly the same. So we can see in code here, we're setting the first part of the tuple to 0, getting the remaining coefficients at random. So that looked exactly like what we did before, but the first one set to 0. Now, when the participants add all the shares they received in this polynomial form, the first coefficients are all 0. So what's going to end up happening is the new polynomial that they create will simply be we'll have all the terms of the polynomial except the first one, since it's 0. And then the participants, they'll take their new aggregate share of this polynomial that has its first term set to 0, and they'll add it to their existing share. And what's going to happen is we'll end up with a share of the sum of these polynomials. Well, when we add these polynomials together, because the second polynomial, that's the FR polynomial, refresh polynomial, because that polynomial, its first term was 0, when we sum the polynomials, the first coefficient term is not going to change. Well, the first coefficient term is our secret. So we have a new polynomial. The other coefficients changed because the new polynomial's coefficient added into the existing polynomial, but the first term stayed the same. And that's exactly what we wanted. We wanted to be able to change the shares, but we want to keep that first coefficient the same. So if you have a polynomial where the first coefficient is 0, you add it to another polynomial, the first coefficient won't change, the remaining terms will. So we'll use our same aggregate shares function, except when we get down to this branch at the end, if there's already an aggregate share, it's not none. Rather than just initializing it to our sum, we're going to add them together and mod by Q. And now everyone will have new shares, but we'll have the same secret. So one thing that's interesting about the refresh protocol is the exact same protocol can be used to disenroll a participant. So let's say we have our 2 of 3. We have Alice, Bob, and Carol, and Alice and Bob want to kick out Carol. They don't want her to be able to sign anymore. They'll run the refresh protocol. Alice and Bob will run the refresh protocol, but they'll exclude Carol. They won't generate shares for her. They'll give each other shares, and they'll aggregate those shares, and those will be their new shares. So now Alice and Bob have shares of this new polynomial with the same secret. But Carol has a share of the old polynomial. So her share is effectively invalidated because it can't be combined with Alice and Bob's shares. Now, a few caveats to this is if Alice and Bob's old shares leak, well, Carol could use one of the old shares with her share to sign or reconstruct the secret. So they actually Alice and Bob have to make sure that they're overriding the old share and it's not leaking out. Another interesting thing about this protocol is our refresh polynomial has 0 as the first term, which means that everybody's learning an extra share of the refresh polynomial. Everybody knows that f of 0 equals 0. Well, that's actually a share of that polynomial. So everybody's learning a free share. And so if we have like a 2 of 3 and Carol gets kicked out, but Carol, for whatever reason, learned Bob's shares of the new polynomial, she would be able to reconstruct the new polynomial because she could take 0, 0 and Bob's new share and derive the new polynomial. And if she has that refresh polynomial, if she has that new polynomial, she could update her own share to the new polynomial. So this is something that's called the adjacent assumption, where we assume that a participant that's corrupted in time period t is also corrupted in time period t minus 1 and t plus 1. If that's not the case, if somehow Carol can learn this this update share that Bob received, then she'll be able to update her share and we'll have a problem. So that's how we refresh and disenroll. Yes, exactly. If it's a 1 of n, a 1 of n, you're going to have a 0-degree polynomial, so everyone's going to exactly, yeah. But if you but for disenrollment, you're really kind of looking at the n, that you're going from n to n minus 1. Yeah. So So let's look at the next brew, which is share repair. Let's say we have Alice, Bob, and Carol loses her share, and she wants to get it back. So we want Alice and Bob to help Carol get her share back, but we don't want Alice and Bob to learn Carol's share. So if we define Carol's X value, her index, as R, the index of the share we're trying to repair, her share can be computed as the sum of a threshold of shares times the Lagrange coefficients evaluated at Carol's index R. Well, before we were evaluating the Lagrange coefficient at 0 because we're trying to get back to the secret. When we plug in f of 0, we get the secret. But if we plugged in f of 3, we would get Carol's share. If we plugged in f of 2, we'd get Bob's share. If we plugged in f of 1, we'd get Alice's share. We can use the Lagrange interpolation to evaluate the polynomial at any x value. So when we want to repair, we want to evaluate the polynomial at the participant's x value that lost their share. And so if Alice and Bob take that value, they take their share, they multiply it by the Lagrange coefficient evaluated at Carol's index, and they split it using additive secret sharing. So additive secret sharing, let's say you have some number and you want to split it into 3 additive shares. Shamir secret sharing is polynomial shares, but there's a different protocol to create these additive shares. With additive secret sharing, you need all the shares to reconstruct the secret. With polynomial secret sharing, you only need a threshold. So we could take any number. Let's say we want to split a number into 3 additive shares, and we're doing this over a finite field. Our first 2 additive shares, we just generate random numbers. And then our third additive share, we take the difference between the secret and the 2 random numbers we created, and that difference is our third additive share. And since we're modding everything by the finite field, it will wrap around as needed, and so we're guaranteed now that these 3 numbers are going to add up to our secret. So Alice and Bob are going to take their share times the Lagrange at R, and they're going to create a number of additive shares with that protocol equal to the threshold. So if in our 2 of 3, Alice is going to create 2 additive shares, and Bob is going to create 2 additive shares. And this is what it looks like in code. So we have our Lagrange coefficient. We give it the indexes of the participants who are participating in the repair protocol, Alice and Bob's indices. We give it the index that we're trying to interpolate, which is Carol's index. And we create these random shares, our additive shares. And then we compute our final additive share as the difference. And then we have, let's say in a 2 of 3, we have our two additive shares. So then they're going to distribute. Oh, go ahead.
So which one is the repair share? Is it S of R or is it S of I multiplied by the Lagrange?
The S of R is the share we're trying to repair. So that would be S sub R is Carol's share. So we have Alice, Bob, and Carol. Carol lost her share. So S sub R is Carol's share. S sub I is going to be Alice's share or Bob's share, because we have I equals 1 through T. T is 2. So we're iterating from 1 to 2, and Carol's index is 3.
Bob need to give the repair information to Carol separately? Like, Bob can't see Alice's repair information, right?
Yeah, well, so that's where this step comes into play, which is first Alice and Bob, they each created 2 additive shares. But then the next thing is they're going to distribute them to each other before Carol gets anything. So Alice is going to keep one of her additive shares and give the other one to Bob. And Bob is going to keep one of his additive shares and give the other one to Alice. And since they each have only one additive share, they don't learn the secret. So that's what this is they're each getting an additive share. Alice is the Z1 and Bob is Z2, and they're each getting an additive share from each other, and then they're going to add those together to get the Z1, Z2. And so we can see that in code here, where again, it's just a very simple algorithm where they're just going to add up the share, their own additive share to whatever additive shares they've received from the other participants to get this aggregate repair share. And then those aggregates, so the aggregate Alice has and the aggregate Bob has, they're going to send those to Carol independently.
If they were to learn the other, then they would have Carol's.
Exactly. So they send those to Carol, and when Carol adds all of them up, she's getting Alice's share times Lagrange coefficient at her index, plus Bob's share times Lagrange coefficient at Carol's index, which is our interpolation formula. So by adding all of these together, we're interpolating Alice's share. We're recomputing Alice's share. But because we did this additive division, Alice and Bob had these blinded values where they weren't able to complete this equation. They each had a part of the equation.
Sorry, but let's say this is a 2 or 3. Let's say if it was like a 3 or 7, then it seems like, and so one of the people lost the shares and they want to repair it. It seems like you need exactly 3 and not more people to participate in this.
You only need 3.
Yeah, would anyone learn extra information like they got from the other?
Well, they can't tell each other their secrets. So like let's say we're doing a 3 of 7, and we need Alice, Bob, and Carol all to participate to recover Dave's share. So Alice, Bob, and Carol, they're each going to now create 3 additive shares, keep one for themselves, distribute the other 2 to everybody else.
What if Edgar also sends them, a share because he thinks he's supposed to be participating in this?
If they need, when they define their Lagrange coefficients, you need to know which participants are going to be involved.
Sure, right. But I'm saying for the repair protocol specifically.
Yeah, same thing for repair. This L1 and L2 and L3. If a new participant gets involved and they didn't actually expect them to be in there, then their Lagrange coefficients aren't going to actually compute correctly.
I guess what I'm saying is, like, what if Alice is malicious and she's trying to get these, aggregate shares from a bunch of them? Does that compromise the security?
As long as you have T honest participants, then you're fine. But if you have T corrupt participants, then game over. But yeah, if you have like if one person's misbehaving, the worst that can happen is that the share the share that you're trying to repair won't actually be a valid share. But they can't actually learn anybody's secrets or anybody's shares. Which is an important point because what we're describing here is actually all in the passive adversary model. If we had an active adversary who's giving bad data and actually preventing Carol from being able to repair, what do we do? Well, we can actually, what we can do here is we can have each participant send a, any participant can compute the committed share of any other participant by taking all the coefficient commitments and evaluating the commitments at somebody's index. The same way we did the share verify protocol, that protocol can be run by anyone. It's all public values. It's coefficient commitments and indices. So Bob can actually compute Alice's G to the S. He can compute her committed share from the coefficient commitments. And they can verify that these values that they received, because or Carol can verify that the values she received are actually that participant's share times the Lagrange, because she can compute G times the share using the coefficient commitments and then multiply it by the Lagrange and see if that's actually what she received from the participant. And so if somebody gave bad data, Carol can actually assign blame to the participant who gave the bad data. And she can also use the same coefficient commitments to see if the share she computed, SR, is actually her share. Because how does she know that's actually the share she had? Well, she can plug in her index into the coefficient commitments and see if that's actually the correct share using that same share verify protocol. Now, one thing that could happen is through all these protocols, the polynomial keeps changing. So the coefficient commitments that were generated in the original DKG may have changed. And also maybe they got lost. So we can actually, a threshold of participants can compute the coefficient commitments using a Vandermonde matrix. So we have this way of expressing a polynomial in a matrix where the first row is the x values at x equals 1. Second row is the x values at x equals 2. Third is for x equals 3. And you can see that when the first row multiplies by the coefficient vector, which is that second, the second vector there, or the first vector, the A0, A1, A2, that equals the shares. It's a way of describing how a polynomial works with matrices. And so if V is our Vandermonde matrix, that left matrix, we say V times the vector A, V, the matrix times the coefficient vector, equals the share vector. Similarly, if A was our coefficient commitments and Y are our share commitments, the share times G, the same equation holds. The matrix times the coefficient commitments will equal the share commitments. So if we want to go from the share commitments back to the coefficient commitments, so we want to isolate A, which is the coefficient commitments, well, all we have to do is divide Y divided by V. So if we take the inverse Vandermonde matrix, multiply it by the share commitments, we'll get back to our coefficient commitments. So as we're changing the polynomial, we can always, a threshold of participants can always figure out what the coefficient commitments are. And then they can use those coefficient commitments to validate the data that we're using in all of these protocols to assign blame if we have an active adversary that is giving bad data. So in code, the repair share protocol is, again, very simple. Carol's going to take the repair shares, the aggregate repair shares that she received from Alice and Bob, add them together, and she'll have her share back. So in the same way that refresh is also the same protocol for disenrollment, repair is the same protocol for enrollment. So let's say we have Alice, Bob, and Carol, and they want to add Dave as a new participant in the Frost quorum. Well, effectively what they're doing is repairing Dave's share that he never actually received to begin with. They just have to evaluate the polynomial at x equals 4, which they can do. Alice, Bob, and Carol can do the repair protocol for x equals 4 and give those shares to Dave, and now Dave has the share at x equals 4. So that's how we add participants. Now, how do we increase the threshold? So one way we could do this is we could run the refresh protocol, but we use a higher degree polynomial for the refresh polynomial. So our refresh polynomial had a 0 term for the first coefficient, and we're adding it to the existing polynomial, so the first coefficient doesn't change. But if that refresh polynomial has a higher degree polynomial, those higher degree terms are also going to add to the old polynomial. And so we could add on, if we had ax to the 0 plus ax to the 1, and we did a refresh polynomial that added an ax squared, well, now when we add everything together, we have a higher degree polynomial. But there's an optimization that's used in this paper where we can do this with less coefficients, so there's less commitments to generate, less EC math to do. It's a slight optimization, because what we're going to do is that's actually supposed to be T prime. So we have T prime minus 2 degree polynomial, T prime meaning the new threshold we're trying to increase to. So one way would be to create this T prime minus 1 degree polynomial with a 0 term for the first coefficient. With this optimization, we're going to do a T prime minus 2 degree polynomial, not with a 0 coefficient, just like all random coefficients. So that's what it's going to look like in code, the same way we've been generating our polynomials. And the difference is now all the participants are going to multiply the share of the new polynomial they receive by their index. So if the new polynomial is g of x, and they each receive an evaluation, participant 1 gets g of 1, participant 2 gets g of 2, well, they're going to multiply that by their index. They're going to multiply the new share they received by their index. And what we're going to get is x times g of x. Well, when we do x times g of x, it's going to increase the degree by 1, because all the x terms are going to get multiplied. X to the 0 is going to become x to the 1. X to the 1 is going to become x to the 2. And we're not going to actually have a coefficient for the first term. So it's this way of taking a t minus 2 degree polynomial and converting it non-interactively into a t minus 1 degree polynomial. And so we have one less coefficient that we need to verify and distribute. Whereas if we did the alternative method of just creating this polynomial with the 0 term and the higher degree, we'd have this extra coefficient. So it's a slight optimization. And we can see this here in code that we're going to sum all the shares of the new polynomial. And then on this bottom line, we see the aggregate share times that participant's index is going to do that adjustment. We're going to increase it by a degree and simultaneously make the first coefficient 0. Then we add everything together. The first coefficient won't change, but the degree of the polynomial will increase. And we can increase it as high as we want in one shot. Like we can go from a threshold 2 to a threshold 10 in one round. So the last brew is the threshold decrease. When we do the threshold decrease, unlike the increase, we can only decrement by 1. So if we want to go from 10 down to 2, we got to keep running this over and over again to decrease it by 1 each time. So the way threshold decrease works is the first part is very similar to our repair protocol. We're going to run the repair protocol, but we're going to choose some random index over the whole number space, because we want to repair a share and then have everybody reveal the share to each other. Everybody's going to learn the new share. So we want to pick an index that would never use for enrollment. So we're going to pick like a random one or a very high one that we wouldn't use for enrollment. And we run our repair protocol, but instead of giving these aggregate repair shares to some new participant like we do for enrollment or for repair, everybody reveals those aggregate shares to each other. So now everybody learns the new share. And that by itself effectively decreases the threshold by 1, because now everybody's got an extra share. But rather than making people keep extra shares around, we want to actually merge all of this into a new share. So we have this equation that we can do to do this. So our new polynomial with the lower degree is going to be f prime of I, and f of r is the revealed share. Everybody knows that value. It's the valuation of the old polynomial at r, our random index that everybody learned. And then we're going to plug in, each participant will take their old share f of I and their index I and apply this equation to get their new share. And this f prime of I, when they do this operation, is going to be a share of a polynomial where the secret has not changed, but the degree of the polynomial is 1 less. So how do we know that this equation actually does this? Well, if we have some f of x and we divide it by a 1 degree polynomial x minus r, that will equal some quotient polynomial plus a remainder d by the polynomial remainder theorem. We know we're going to get a polynomial, and we know maybe there'll be some remainder left over. Now, if we can manipulate that equation by multiplying each side by x minus r, and we can see here that if our x is equal to r, then f of r will equal d, our remainder. Because when we plug in r, we're going to get r minus r, which is 0, times the quotient polynomial. So f of r equals d. Therefore, f of x minus f of r equals x minus r times the quotient polynomial, because we just subtracted out the remainder. Because we know the remainder is f of r. So when we subtract f of r, the d goes away. And then we can isolate the quotient polynomial. We can compute that by itself. Q of x equals f of x minus f of r divided by x minus r. We just divided the x minus r from both sides. So if we take that equation we just arrived at and we plug in 0 for x, we're going to get this q of 0 equals f of 0 minus f of r divided by negative r. The x just dropped out because it's 0. And if we isolate f of 0, so we just manipulated this equation so we get f of 0, we see that f of 0 equals f of r minus r times q of 0. So if we define our new polynomial f prime of x as this f of r minus r times q of x, we know that the secret hasn't changed, because we know that when we plug in 0, we'll get f of 0, and our secret is f of 0. And we also know that this here is a t, if our original polynomial is t minus 1 degree, we know when we do this division, we're going to get a t minus 2 degree polynomial, because we're dividing out an x. So we're moving the degree down 1. So, and those are the two properties that, that we needed to prove. One, that the secret didn't change. F prime of 0 equals f of 0. And that that f prime of x is now a t minus 2 degree polynomial. So we decreased the degree of the polynomial by 1. And we can see that in code here, where our numerator is our share minus the revealed share. The denominator is our index minus the revealed shared index. That's how we get the fraction. We compute the quotient, and then we take the revealed share minus the revealed share index times the quotient. So that's just our formula there on the left in code, and we're using the modular division over the finite field, and we've decreased the threshold. And again, we can use our Vandermonde matrix and the coefficient to figure out coefficient commitments, and all of these outputs for all of these protocols can be verified against the commitments. So if anybody's submitting faulty data, they can be proven to have submitted bad data. We can disenroll them from the protocol and proceed as we need. So that's it. That's all I've got. Does anybody have any questions?
So if a share is compromised, apologies if you already covered it, but you would just disenroll them and then make a new share by increasing the enrollment. And have you lost anything? Has the bad guy gained any information?
So if, let's say we have Alice, Bob, and Carol's share was compromised, then you could you would just run the refresh protocol. So Alice, Bob, and Carol would get brand new shares, and the compromised share would no longer be useful. And so, yeah, that's effectively. Or if you're in a situation where Carol had a share on her phone and she lost her phone, and you don't know if it's compromised or not, the first thing you would do is you'd get Carol back her old share that might be compromised. You'd run repair so she gets her old share back. And then you'd run refresh So now that the old share is invalidated.
Would it be prudent to refresh periodically? Is that like?
Yes, absolutely. And depending on the environment, like if everybody's online, you can refresh a lot. If you have an offline signer, then you got to wait for them to be available to participate in the protocol.
But the bad guy who perhaps is observing one of the signers, say the whole time, say you were never clued in that it was compromised, isn't gaining anything over time. He only ever has one share.
Right. So as long as the attacker is not able to get T shares within the time period before they've refreshed, then he starts over. Exactly. So and so the more often you refresh, the harder you're making it for that attacker, that they have to compromise more within a shorter time period. Whereas if you're refreshing every 10 years, then they have 10 years to get a threshold before having to start over.
Does that introduce problems of it's hard to delete keys and how to actually delete it for the other shares?
Well, it depends. I mean, you already need T honest participants for the security of the protocol to hold, because if T participants aren't honest, they can just recompute the secret. So if they're intentionally not deleting, you could have a participant who isn't colluding with other participants to reconstruct a secret, but is misbehaving by not deleting. Now, what is their incentive to do that? It's not quite clear, like, how they would benefit from that exactly. So if they're honest participants, they'll probably at least try to delete the old share. Now, whether that's actually successfully deleted or not, is another issue. And if you have an environment where like you have a single wallet holder who has their share split among different devices, they're going to have every reason to try to delete stuff because they want to protect their secret. If you have maybe a bunch of participants who don't trust each other, like some kind of shared UTXO thing or something like that, then maybe a participant wants to gain some advantage and wants to hold on to the old data because they think that might be useful to them. So then the question is, how can they actually benefit from holding on to the old share? And I don't really think they can. One thing they might want to do is well, what if I get disenrolled? But I don't think the old share would help them, because even if they have a bunch of old shares, when disenrollment is run, they're not going to be part of that new polynomial, and all their old shares will be invalidated. So there's not a big incentive to purposefully hold on to the old share, but it's definitely a risk. And when you combine that with the adjacent assumption, where everybody's getting this free 0-0 share, and they can, with one less than the threshold, they can reconstruct the refresh polynomial and convert an old share to a new share. That's where an old share potentially could be valuable. If you take an old share in combination with learning a refresh polynomial, then you can update that share to the new polynomial. So now there is a newer protocol that removes the adjacent assumption. What it does is, for the refresh protocol, you use a higher degree polynomial. You do it 1 degree higher. And that way now the 0-0 share isn't is sort of negated out because you have a 0-0 share of a higher degree polynomial. And then when you're done with the refresh, you run this polynomial truncation protocol to now reduce the polynomial back down to your original threshold. So if you do that, you remove the adjacent assumption. You don't have this issue of t-1 participants could compute the refresh polynomial. And that really makes it so that those old shares aren't very valuable because there really isn't an avenue anymore to update them to the new polynomial unless you have t participants working together to do that. And if you had t participants doing that, they might as well just compute the secret and take all the money. But definitely a lot of surface area and complexities and things to consider here. And a lot of this is kind of uncharted waters, especially when you think about combining all these protocols together. It's not like we don't have like a meta protocol that defines all of these into a single protocol where you're combining frost and threshold increase and decrease and enrollment and all of that and showing, maybe there would be some surprising interactions where if you do one and then the other, or what order should they be in? Do you do enrollment first and then the other one first? It would be nice to be able to do these things atomically where you could, increase the threshold and add a participant in a single operation. So you have to think carefully about how is the sequencing going to work. And using the Vandermonde matrix to kind of keep the coefficient commitments around and do these validations, that's not really documented in the literature. So yeah, there's going to be like subtleties and nuances to consider with how to actually use this stuff safely.
Gennaro, TSS. This seems a lot simpler than that.
Thank God.
It's pretty similar. Yeah.
But it seems somewhat simpler. But maybe that's just because the details are the details. I know you mentioned that you need a proof, like a zero knowledge proof, one piece of that setup.
Right, which is not in the Gennaro scheme, is the proof of knowledge.
Right.
But other than that, it's almost the same distributed key generation in Frost and those prior schemes. The difference being the proof of knowledge, and in the Gennaro scheme, there's a robustness part of the protocol where you can keep proceeding through the distributed key generation even if some of the participants aren't behaving. You then compute the share of the participant who misbehaved and you can keep moving forward. In Frost, they removed that where they basically just had if anybody's misbehaving in keygen, start the whole thing over. So that makes it a little bit simpler. And then we also have roast is another way of getting robustness by wrap Frost in a higher level API that also is makes it a little bit more complex. But they're basically, if you squint, kind of essentially the same thing, just with these slight differences.
It's interesting because Gennaro the updated one was 2018, but this was 2017.
No, this is Frost is 2020, I think, or something like that. It's definitely the latest one. And then there's also Frost 1, Frost 2, and Frost 3. So it's been iterated on. And then even before Gennaro, that was based on Feldman VSS and, this basic concept of doing these multiple polynomials and adding them together has been around for a while. And all these protocols, a lot of them go back to the 90s before distributed key generation, that they were just developed for trusted Shamir secret sharing setups. So that's kind of what's new about this is we're kind of taking these protocols developed for Shamir and now applying them to Frost.
For some brews, like the
share repair, it says it's direct communication between those involved is required, right? So on practical level, so does it mean that for every participant they need to have a direct connection to each other, or can it be like all funnels with that?
I mean, you use enrollment, right?
Oh, yeah.
Right. Each participant needs to have a secure channel, right? So they each need to have some kind of a secure channel with each other participant. Now, you could implement that secure channel through like a server that's just hosting data and allowing people to pull it down, as long as each participant has like an authenticated public key exchange with each other participant. Then you could use Diffie-Hellman and authenticated encryption algorithm so that everybody can encrypt data to each other participant. But they're definitely transmitting secrets to each other that no other participant should learn. Yeah.
Trying to kind of tie this back for myself, but it seems like there's like a lot of moving pieces with all the brews, like the share repair, the enrollment, like the refresh, all this kind of stuff. So there's like a lot of moving parts. What's like the immutable piece of it that's actually kind of getting tied back to like the on-chain ledger? I'm assuming there's like a UTXO that it all kind of funnels back into. Is it the original polynomial?
Yeah, it's actually the original. The first coefficient of the original polynomial. That's your private key. And that's what is securing the UTXOs on chain. And you can do BIP32 derivation too, where you can derive child keys and so on. But that first coefficient, that's the thing that can't change. The rest of the polynomial can change. All the other coefficients can change. The degree of the polynomial can change. You can get more polynomial shares and evaluations, but as long as that first coefficient does not change, you're good, which is why we keep having to either add 0 for the first term or prove that f of 0 is in the new polynomial is the same as the old polynomial. It's that f of 0 evaluation that has to stay the same.
Yeah, I mean, I know there's some Schnorr sharing implementations that don't put the secret at 0. They put it somewhere else. I'm guessing this doesn't work at all with that.
Yeah, I'm not familiar with those. Maybe there's a way to make it work. I don't know the details of how that would work. But wherever the secret is in the polynomial, it's like that's the term that can't change and everything else, can. Yeah, I'm not sure. Any other questions?
So what was the name of the protocol that does not have that adjacent vulnerability? You said there's a new protocol.
Yeah, that comes from this paper. This paper here, which was published a few years ago, or 2019, provably secure proactive secret sharing without the adjacent assumption. And so that's the protocol where you do the polynomial truncation, where first they do a refresh with a higher degree, and then there's this distributed way to truncate the polynomial, also using a similar thing that we did with getting the coefficient commitments back, where you use some matrix multiplication to truncate the polynomial. So definitely a nice improvement on the existing scheme.
Decreasing the threshold, could it be possible to go multiple degrees at the same time, the way you would go, this the example that you said, from 2 to 10. So here also you can go from 10 to 2 in a single step.
Yeah, that is an interesting possibility that's not actually discussed in the paper, but it does seem like if you have a method of truncating the polynomial, that could be used to decrease the threshold and might actually be a preferable way to do it. So an interesting place to explore is, can we use this technique for that other purpose? And I suspect the answer is yes.
Like proof of concepts out there? Are there actually any not production implementations, but are there? I guess where it is, right?
Yeah. So in terms of the base Frost protocol, so I have my non-production ready Python implementation here, and this Python implementation has all the brews that we went over today. It doesn't have all the some of the verification on threshold increase and decrease and stuff, which I'm going to be adding, but it has almost everything we discussed. It doesn't have that paper we just talked about with the newer method that removes the adjacent assumption, but planning on adding that at some point. And now in terms of the base Frost protocol, we have, there's an implementation in Lloyd's repo secp fun. He has a Frost implementation. I have a PR open in secp-zkp that implements Frost on top of secp, on top of Bitcoin's secp implementation. And there's a PR open in the Zcash Frost repo for a Taproot support in their implementation that should be getting merged soon. Zcash also has implemented the repair protocol, and they have issues. They have it on the roadmap to implement refresh, I believe. And there's been some discussion in the repo about also the changing the threshold and some of that stuff. So I expect to see that make its way into the Zcash repo. And once we get the secp PR merged, I plan on adding the brews to that implementation as well. But if anybody wants to play with this stuff for the hackathon, the Python one is ready to go. It will do a valid BIP32 signature that will verify, and happy to help with any projects that want to play around with this. All right, thank you.